This is an introduction to plate tectonics. On the left side, you see a breakdown of the Earth according to chemical composition. The crust is composed primarily of silicate minerals. The mantle is made up of ultramafic silicates, and the core primarily iron-nickel alloys. The crust ranges from 5 to 150 kilometers thick. A kilometer is 6/10 of a mile, so the crust ranges from 3 miles to 90 miles thick. That is, the distance from our campus to downtown Aiken and the distance from Augusta, Georgia to Camden, South Carolina. Oceanic crust is thinner and made up primarily of iron and magnesium-bearing silicate minerals. These are called mafic minerals, and they are dark in color. Crust rich in iron and magnesium-bearing minerals is said to be mafic. Continental crust is thicker and made of minerals rich in sodium, potassium, aluminum, and silica. The feldspar minerals and quartz, or silica. Crust of this composition is said to be felsic. The mantle is composed primarily of olivine. Olivine is a mineral very rich in iron and magnesium, and so the mantle is said to be ultramafic. The birthstone for August is peridot, a gem variety of olivine. A rock composed entirely of olivine is called peridotite. Peridotite is composed of glassy green grains of olivine. Peridotite and dunite are synonyms for ultramafic rocks. Wherever these ultramafic rocks crop out on the Earth's surface, geologists are interested in them. In the study of plate tectonics, it's more helpful to break down the Earth into layers with different physical properties, or how the rocks respond to deformation. The crust and the uppermost mantle make up what's called the lithosphere. There's oceanic lithosphere and continental lithosphere. The lithosphere is rigid. If you can imagine pushing on the edge of a table and making the whole table move, the lithosphere is rigid, like that. Rigid lithosphere transmits stresses. The lithosphere floats on the asthenosphere. The asthenosphere is soft and flows. The asthenosphere is slowly deforming, slowly flowing mantle material. I'd like for you to think of the lithosphere floating on the asthenosphere like leaves floating on water flowing in a gutter. The leaves will move anywhere that the water takes them. The lithosphere moves anywhere the flow of the asthenosphere carries it. The lithosphere is broken down into about a dozen major lithospheric plates. Think of the broken shell on a hard-boiled egg when you think of these lithospheric plates. These plates move relative to each other. There are 3 ways that these plates can interact with each other. 2 plates can move apart from each other. 2 plates can come together. 2 plates can move horizontally alongside each other. When the plates move apart from each other, this is called a divergent plate boundary. When 2 plates come together, this is called a convergent plate boundary, or sometimes subduction. When 2 plates move horizontally alongside each other, this is called strike-slip or transform plate boundary. It's important to notice that plate boundaries don't always correspond to the edge of continents. For example, look at the North American plate. The western side of North American plate corresponds to the western coast of North America, but the eastern edge of the North American plate is far away from the edge of the North American continent. The eastern edge of the North American plate corresponds to the Mid-Atlantic Ridge. In this drawing, red lines correspond to divergent plate boundaries, green lines correspond to convergent plate boundaries, and black lines correspond to transform plate boundaries. Volcanoes and earthquakes are localized on plate boundaries. In the upper left diagram, blue dots are earthquake locations. Red triangles correspond to active volcanoes. In the lower right, different ocean floor features correspond to different plate boundaries. Divergent plate boundaries correspond to ridges on the ocean floor. Convergent plate boundaries correspond to deep-sea trenches on the ocean floor. Transform plate boundaries correspond to oceanic fracture zones. This cartoon shows the 3 sorts of plate boundaries: a divergent plate boundary where two plates are moving apart at an oceanic ridge, a trench where ocean floor crust is being subducted beneath continental crust in this drawing, and fracture zones separating segments of the spreading ridge. Notice mountain ranges and volcanoes form above the subducted ocean floor lithosphere and landward of the trench. The volcanoes form by partial melting of the subducted plate and the mantle that overlies it. It is thought that plate motion occurs as a result of convection in the asthenosphere. Hot mantle material rises at a divergent plate boundary or oceanic ridge, and cold mantle sinks at a convergent plate boundary or trench. In this drawing, hot mantle material is rising at the mid-Atlantic ridge and sinking at the west edge of South America, where the Andes are forming today. The Red Sea is a modern example of a young divergent plate boundary, where Egypt is pulling away from Saudi Arabia. Along the Red Sea, a particular sort of volcanic rock called basalt is erupted at a divergent plate boundary. If you want to know what the Atlantic looked like 150 million years ago, at a time when North America began moving away from Africa, the Red Sea is a good model for that. The Atlantic has taken 150 million years to grow to its current width. The rate that continents move apart at a divergent plate boundary is about the same as the rate that your fingernails grow, tens of millimeters per year or centimeters per year. Basalt is a black volcanic rock that flows very easily. Basalts make what are called shield volcanoes. When basalt is erupted underwater, it makes particular structures called pillow basalts, where glassy rind surrounds a coarser-grained core. The glassy rind forms where lava chills in contact with seawater and then inflates with lava, just like a balloon. In this picture, a man is sitting on a boulder beneath a cliff that is made up entirely of pillow basalts. Pillow basalts were first observed forming at the Mid-Atlantic Ridge in the 1960s. Today, when a geologist sees pillow basalts, he interprets that these rocks formed as undersea volcanic eruptions. This drawing shows what happens at an oceanic trench. Cold lithospheric material, colored violet, lavender, and blue here, is carried deeper and deeper in the trench beneath the overriding plate. Friction between the overriding plate and the subducted plate results in earthquakes and faulting. These earthquakes are shown by red dots in the diagram. This zone of earthquakes dips away from the trench and beneath the overriding plate. A convergent plate boundary is recognized in the northwestern United States and southwestern Canada. The Juan de Fuca oceanic plate is being subducted beneath the North American plate. Barbs are drawn on the overriding plate. This has resulted in the formation of the Cascades Range. The labeled peaks shown on this drawing correspond to andesitic volcanoes that formed as a result of subduction of the Juan de Fuca oceanic lithosphere and partial melting of the subducted ocean floor crust and the mantle wedge above it. Andesitic volcanic rocks look different from basalts, and andesitic volcanoes have a very different form from basaltic shield volcanoes. In general, andesitic volcanoes form by explosive eruptions and have a very characteristic cone shape. Andesitic volcanic ashes are easily eroded and sometimes leave behind the igneous rocks that crystallized in the neck or the throat of the volcano. In this picture in the lower right from Shiprock, New Mexico, in the Four Corners region of the southwestern U.S., you can see the system of volcanic necks and dikes that extend from the main volcano. Folding and faulting of rock layers both accompany convergent plate motion. In this picture from the Calico Hills near Barstow, California, you can see the folding of rock layers above the parking lot. The valley and ridge pattern of hills in the Zagros Range of northern Iran shows folding of rock layers very much like what is seen in central Tennessee or central Pennsylvania in the U.S. Appalachians. In this photograph from southwestern Nevada, Older rocks that have a distinct vegetation are thrust over unvegetated, white, younger rocks along a feature called a thrust fault. In my work as a geologist, I trace out the distribution of these different rock types on topographic maps and aerial photographs. Different colors correspond to different rock types on this map. In this way, it's possible to recognize folding at the map scale over tens of miles. To the left is shown the sequence of events that rocks undergo between folding and faulting. On the right is sketched a single purple layer that looks like a rumpled wet towel. The purple layer represents a single rock layer complexly folded over a great number of miles. By tracing out this rock layer in the field, it's possible to recognize very complex fold structures. It's easy to see these sorts of structures in an area with a lot of topographic relief, or a large difference or elevation change between the high peaks and low valleys, as in the Southern Canadian Rockies or in the Alps. In conclusion, the Earth's crust and uppermost mantle form the lithosphere. The rigid lithosphere floats on a asthenospheric mantle and is carried by convection currents within the asthenosphere. Relative movement between different lithospheric plates results in three different types of plate boundaries: divergent, convergent, and transform. Each of these plate boundaries correspond to different ocean floor features. Divergent plate boundaries correspond to oceanic ridges, convergent plate boundaries, oceanic trenches, and transform plate boundaries, oceanic fracture zones. Divergence at oceanic ridges results in eruption of pillow basalts. Seafloor spreading rates are comparable to fingernail growth rates. Convergence at oceanic trenches results in earthquakes and andesitic volcanism. Mountain ranges typically form landward of the trenches. Folding and faulting accompany mountain building at convergent plate boundaries. Thank you.